Try and stand a pencil up on a desk with its pointed end facing down. If you can stand it perfectly upright, it may be balanced enough not to fall over. Hold it as straight and perpendicular as possible. But it's not so easy. However straight you stand the pencil up, it will always fall over. It doesn't matter how many times you try or how perfectly vertical it is. You may think this is obvious, but it was this seemingly insignificant phenomenon of the falling pencil that led to a major scientific discovery. The 2013 Nobel Prize for Physics put the Higgs boson in the spotlight. When the existence of the Higgs boson was confirmed at a massive experimental facility, it was hailed as the discovery of the century.
We've always wondered about what's going on in the sky, and today we've made remarkable progress. We understand a great deal about our universe. It's the last straw, so to speak. It's the missing ingredient. It's either the beginning or the end of an era.
The deep connection between the Higgs boson and the falling pencil was discovered through research of great importance in the field of modern physics. For over a century, starting with Einstein, physicists have wondered what this universe is made of. They have asked, if the universe had a creator, what kind of blueprint would have been used? Their goal was to discover this blueprint of the universe and, using the language of mathematics, express it as a formula. To date, physicists have successfully come up with formulae to express various natural phenomena. But if they could find just one formula to describe all the phenomena in the universe, this would surely be the ultimate formula. Physicists have long been fixated by the quest for the ultimate formula.
There should be equations which have a precise meaning. They should be elegant, simple, and we solve the equations and we account for the phenomena of nature. The goal is that we will have one beautiful theory, that it will all come together.
What is this universe made of? The search for the ultimate formula has been a long and arduous road. But the search for a formula of perfect beauty resulted in the paradoxical conclusion that it was mathematically impossible for the universe to exist. And this is where we come to the idea of the falling pencils. It's suggested that in the real world, perfect beauty was destined to fall apart. And it led to the discovery of the Higgs boson, as well as opening the way for the ultimate formula. But the ultimate formula proved elusive. This is the story of the century-long struggles faced by the pioneering physicists in their quest to discover what this universe is made of and what forces govern it. You may be surprised to hear that in the last 100 years, physicists have in actual fact come very close to discovering the ultimate formula. Outside the huge experimental facility where the Higgs boson was discovered, there is a stone engraved with a formula. That's right. This is the cutting-edge formula that physicists believe to be the closest they've got to the ultimate formula. It may look impossible to understand, but don't worry. Written in more detail, the formula looks like this. The first line is a formula that describes the properties of the smallest known units of matter in this world, known as elementary particles. These elementary particles are divided into 4 types. Let's see where these elementary particles can be found. Being the smallest units of matter, they exist at the ultimate micro level. Firstly, there are the electrons that orbit around inside an atom. You are probably familiar with them. Next, there are the 2 types of elementary particles known as quarks that make up the nucleus at the center of the atom. Lastly, we have neutrinos, capricious particles that fly out of the nucleus from time to time. What then causes these elementary particles to stay inside atoms or to move about? The answer lies in these 3 lines. Going back to the atom, what's drawing the electrons to the nucleus is electromagnetic force. Gathering together the 2 types of quarks and creating the nucleus is what's known as strong force. And what is causing the neutrinos to jump out of the nucleus is weak force. Physicists believe that if they had a complete understanding of the 4 elementary particles and these 3 forces, they would be able to explain everything in this world. The last 2 lines refer to the existence of the Higgs boson. We will learn what role this particle plays later on. How did physicists arrive at the formula thought to be the closest to the ultimate formula? Let's take a look at their epic journey spanning 100 years. Starting at the top, the first line is a formula that explains elementary particles, the smallest units of matter. Behind this formula lies the story of one man who insisted formulae must always have beauty. Our story of the quest for the ultimate formula starts here in Cambridge in the late 1920s. A young physicist lived here at the time. His name was Paul Dirac, a genius in his field at just 30 years old. He was appointed Cambridge University's Lucasian professor, one of the most prestigious academic posts in the world. Scientists who have held this position include such renowned figures as Isaac Newton and Stephen Hawking. With the goal of finding a formula that would explain everything, Dirac first focused on electrons, the only elementary particle to have already been discovered. At the time, the properties of electrons were described by a formula known as the Schrödinger equation, and it was possible to calculate their energy. But it became apparent that there was a certain feature of electrons that could not be explained by the Schrödinger equation. It was the fact that, like Earth, electrons spin on their own axis, and that they also had magnet-like properties. In his attempt to find a formula that would explain the mysterious properties of electrons, Dirac took a bold approach. At the time, scientists used results from experiments and observations to devise new formulae. Dirac, however, decided to follow his sense of aesthetics. Physical law should have mathematical beauty. This was Dirac's motto. That's right, beauty. You may think this all sounds rather vague for a scientist. After all, some people may think this kind of scenery is beautiful, while others will see this as the height of beauty. Beauty is in the eye of the beholder. But for physicists, beauty equals symmetry. It is measured against very specific criteria. We can explain what physicists mean by beauty using this drawing board. For example, take these two diagrams. Physicists would not hesitate to describe the diagram on the right as being beautiful. You may think this is obvious, seeing that it's a perfect circle, but there is more. Physicists use x and y axes like these as coordinates to assess beauty. Let's look at the formula for a circle in terms of these axes. When we rotate the axes like this, the formula does not change. This is what makes it remarkable. The formula is said to have rotational symmetry, and physicists think of this as beautiful. Physicists also love striped patterns like this. This is because even if the axes are moved, the formula expressing the stripes does not change. In such instances, physicists call this kind of beauty translational symmetry. A formula is beautiful if it looks the same, even when the axes are changed, or in other words, the point of view is changed.
A symmetry is simply a statement that something looks the same from different points of view. For example, a square looks the same when you change your point of view by 90 degrees. They're statements that the laws of nature don't change their form, their content, when we change our point of view in certain definite ways.
There was another type of beauty that Dirac valued greatly: Lorentz symmetry. It is related to Einstein's theory of relativity, and it describes how time and space are in essence the same. Working from this, Dirac came to the following conclusion. If there was such a thing as a blueprint for the universe, it would surely have a perfect beauty. That is to say, it would display all the different types of symmetry. Now, let's look at the Schrödinger equation again. If you look at it closely, you'll see that there is a t that represents time and an x squared, where the x represents space. This means that this formula does not have Lorentz symmetry, where time equals space. As a result, when seen from a different point of view, the formula changes its form significantly. And so Dirac started working on a formula that would possess all types of symmetry. He locked himself away in his study for 3 months, and cut off all contact with the outside world. He alternated constantly between feelings of elation and fear, and he was often overcome by panic. But his struggles and his dedication to the idea of beauty paid off in the end. This is the paper he published in 1928. In it, he presented the Dirac equation. There is one t and one x. It was a simple formula that possessed even Lorentz symmetry. The equation was remarkably effective. It succeeded in accurately explaining even the mysterious properties of electrons, including their spin and their magnetism.
It was gorgeous. It was beautiful. I cried. I cried. Many physicists cry when they see the Dirac equation, because they see the theory of the electron, so bizarre and random, so many pieces to it, and all of a sudden, because of symmetry, it whoop, goes into a single theory.
Furthermore, the Dirac equation was subsequently found to also be applicable to neutrinos and quarks that were discovered later.
The equation has these tremendous symmetries which otherwise were not obvious, and so it actually helped enormously to get people thinking about symmetry in general.
The first line on the stone engraved with the ultimate formula shows a simplified form of the Dirac equation. What is the world made of, and what forces govern it? Physicists have strived to find one formula that could answer this question. The next challenge they faced was to find formulae for the three forces that brought particles together and moved them about. First to be tackled was the most familiar out of the three forces: electromagnetic force. Electromagnetic force draws electrons to the nucleus. It also brings together atoms to create various substances. In the 1930s, there was a physicist on the west coast of the United States who sought to find a formula for electromagnetic force. This physicist was Robert Oppenheimer, who later became known as the father of the atomic bomb. He was gaining recognition across a whole range of research areas.
He knows all aspects of physics. He has amazing powers of synthesizing, of understanding what is going on.
Oppenheimer and his contemporaries focused their attention on the fourth type of symmetry, gauge symmetry. Gauge symmetry is a difficult concept. Put simply, it is similar to rotational symmetry. It describes a kind of beauty where if there were a protractor in every point in space that measured the magnitude of electromagnetism, the formula would stay the same, even if the angle changed. The physicists sought to develop a formula that possessed the four types of mathematical beauty, including gauge symmetry. Then a formula emerged once again. This was, so to speak, an evolved version of the Dirac equation, which possessed all four symmetries and could explain the properties of electromagnetic force. The formula described a fascinating world. Electrons emit particles of light called photons, which connect the electrons to the nucleus. The idea was that it was particles that carried the force.
When he found that some physical quantity were calculated and were infinite, made no sense at all.
When calculations were made, the results suggested that the energy of electrons was infinite, which would mean that all matter could not exist. Why did the calculations produce these incomprehensible results? Oppenheimer and his colleagues redid the calculations over and over again, but they were unable to resolve the problem of infinity. Meanwhile, the world had been thrown into turmoil. In September 1939, Germany invaded Poland, and the Second World War began. Furthermore, the American physicist Enrico Fermi succeeded in producing a nuclear fission chain reaction using uranium. This led to many physicists becoming involved in the development of the atomic bomb. Oppenheimer, the brilliant physicist from America, was appointed director of the Manhattan Project. Physicists gathered in Los Alamos, in the state of New Mexico. And so, the research to find the ultimate formula faded away without ever solving the problem of infinity. The atomic bomb killed hundreds of thousands of lives. The press branded Oppenheimer the father of the atomic bomb. He was never to return to the forefront of research in electromagnetic force. Could Oppenheimer not have gone down a different path that would have kept him in the pure world of theoretical physics? In 1948, as Oppenheimer wrestled with his conscience after the war, he received a letter from an unlikely source. The letter had been sent by Shinichiro Tomonaga, a Japanese physicist he had never heard of. Tomonaga wrote, "During the war, I had found a way of resolving the problem of infinity. However, the chance to present my findings to the Western world was taken away from me." Oppenheimer was moved by this unexpected message sent from a country victimized by the atomic bomb he designed.
Oppenheimer immediately recognizes the importance of what had been done in Japan, sends the letter that Tomonaga had sent him to all the participants, and asks him to write up an article to be put in the Physical Review so that it's more widely disseminated.
Tomonaga's paper was translated into English, and with Oppenheimer's help, it was published in the world-renowned Physical Review. The world was astonished by the paper, which presented a unique calculation method that successfully defeated the problem of infinity. One American physicist described the situation in the following way.
Somehow or other, amid the ruin and turmoil of the war, totally isolated from the rest of the world, Tomonaga had maintained in Japan a school of research in theoretical physics that was in some respects ahead of anything existing anywhere else at the time. It came to us as a voice out of the deep.
Around the same time, two American physicists presented an equivalent theory to Tomonaga's. Amid the sense of freedom that followed the war, the problem of infinity was quickly resolved. The formula developed by Tomonaga and the others produced calculation results that matched experimental findings to an astonishing degree. One example of this is the strength of the electron's magnetism. This is the figure produced by the formula that the pursuit of the beauty of symmetry finally created. This matches the experimentally observed figure right down to the 10th decimal place. By staying faithful to the beauty of symmetry, the correct formula can be developed. This is the second line of the ultimate formula that physicists discovered. A staggeringly accurate formula left its mark on history. And so the formula for electromagnetic force was finally found. But as we enter the 1950s, an unexpected fate befalls the physicists striving to discover the ultimate formula. Caught up in this new setback was Chen Yang. As you will recall, there are three forces that govern the movements and behaviors of these elementary particles. The formula has already been discovered for the electromagnetic force that draws electrons to the nucleus. Yang focused his attention on the strong force that holds together the quarks making up the nucleus. He also looked at the weak force that makes neutrinos fly out of the nucleus. Again, it was the beauty of symmetry that guided Yang in his quest to find the formulae for these forces.
I thought there must be some fundamental principle. And I realized that for electromagnetic interactions, there was a fundamental principle.
Yang decided to see if there was something akin to the beauty of gauge symmetry to be found inside the nucleus. His search resulted in a challenging concept, even for the most capable physicists, known as non-commutative gauge symmetry. In 1954, Yang and his colleague Mills published a research paper. By incorporating a new type of gauge symmetry, they had succeeded in developing a formula for a force that exists between particles.
It was like the Maxwell equations, except that it was more elegant and a tighter kind of symmetry. Yang-Mills was the next thing beyond quantum electrodynamics.
Taking Young's theory and expressing it in the language of contemporary physics, we get a formula like this. And now, we have what physicists believe are the components that come closest to the ultimate formula, except for the part relating to the Higgs boson. But there was another surprise waiting for them. It was a paradox that saw the mass of the particles that carry strong and weak forces end up as zero, however it was calculated. Only photons were known to be massless, and all other particles, such as the W and Z, were supposed to have mass.
The photon was known to be massless, had been known to be massless since the beginning of the 20th century. The W and the Z, when this theoretical work was done, had not yet been discovered, but it was clear because they hadn't been discovered, that they had to be very heavy.
Young's formula possessed real beauty. However, it suggested that force carrier particles were massless, and so it was clearly divorced from reality. Physicists had devoted themselves to the pursuit of perfect beauty, but the problem of zero mass presented them with an inescapable paradox. And there were more surprises in store for the physicists. Further advanced research in symmetry led to the remarkable suggestion that it was not just the force carrier particles, but all elementary particles which make up the smallest units of matter that were found to have zero mass, at least according to formulae. In other words, everything in this world is massless. This was the impossible conclusion drawn from mathematical formulae. If all elementary particles really did have no mass, we would be in a lot of trouble. According to the calculations, electrons would fly out of atoms and all matter would fall apart.
All of a sudden, had all its atoms turned to a state of perfect symmetry where everything had zero mass, first of all, it would fly apart. All the particles would fly out at the speed of light. And there's no stable matter, no people, no dogs, cats, no cities, because things are always moving, and there's no stable matter to create atoms.
Oh dear, things are looking serious now. How to tackle this mystery of mass that had suddenly emerged? In the 1960s, a completely new type of physicist appeared on the scene in Chicago, in the United States of America. His name was Yoichiro Nambu, originally from Japan. This is what people said of him. Nambu can see the future. This maverick physicist came to resolve the great paradox of mass equaling zero in the presence of mathematical beauty. In the early 1960s, what Nambu was most interested in was this phenomenon. That's right. It was the problem of the falling pencils we saw earlier. A pencil falling over may seem insignificant to you, but it was precisely this phenomenon that Nambu knew would help solve the problem of zero mass. You can think of it like this. Let's say there was a blueprint for a pencil that stands upright. The blueprint tells you to stand the pencil upright, and so it calls for rotational symmetry. What happens if you do as the blueprint says and try and stand the pencil? In reality, the rotational symmetry called for in the blueprint cannot be achieved. Even though there is symmetry in the blueprint, this symmetry is lost in the phenomenon that we see in reality. This is the phenomenon known as spontaneous symmetry breaking, a concept that later garnered a Nobel Prize. It occurred to Nambu that this spontaneous symmetry breaking might also be found in the blueprint for the natural world.
This was originally the work of Yoichiro Nambu, that it's possible to have symmetries of the laws of nature that are still not respected by the physical phenomena.
In 1961, Nambu presented a research paper on strong force. Using the language of contemporary physics, the paper can be summarized like this. This is a formula that describes the properties of strong force. In other words, it is a blueprint for strong force. Written in more detail, it looks like this. We can now see the quirks that feel strong force. This blueprint is designed to follow a type of gauge symmetry. As a result, the mass of quirks must be zero. But as we saw with the blueprint for the pencil, which had rotational symmetry yet gave rise to a reality without rotational symmetry, Nambu realized that the blueprint where quirks have zero mass must result in a reality where quirks do have mass.
I didn't notice the breaking of symmetry right away. It was a solution I arrived at after a lot of thinking. In hindsight, I realized it was an obvious phenomenon.
This is a simple summary of what Nambu worked out. Having pursued perfect mathematical beauty, physicists were met with the paradox of zero mass. But using the falling pencil as an example, Nambu succeeded in showing that perfect beauty was destined to fall apart, and therefore give rise to mass in this world. The everyday occurrence of a pencil falling over led to the concept of spontaneous symmetry breaking. It was a major discovery that no one could have predicted. At last, it's time for the Higgs boson to make its appearance. Taking their cue from Nambu's concept that explained the mass of quirks, physicists next try to attribute mass to electrons, neutrinos, and weak force particles.
At the University of California at Berkeley,
Steven Weinberg is a professor at the University of Texas. He was working on the idea of using Nambu's concept of spontaneous symmetry breaking to show that, like quirks, the other elementary particles also have mass. And finally, he ventured into the forbidden zone that no other physicists had dared to enter. He decided to introduce to his theory a convenient particle that not a single person thought could possibly exist in this world.
the theory of Salam and myself introduced a new field, a new kind of force into the theory, a field that acquires a value in empty space, even far away from any source, and in fact that pervades the universe. And this is the field that breaks the symmetry.
This was the research paper that Weinberg used as reference at the time. It was written by no other than Peter Higgs, who won the 2013 Nobel Prize in Physics. The paper stated that if the elementary particle, the Higgs boson, were to conveniently exist, mathematically beautiful symmetry would spontaneously break. Elementary particles and force carrier particles would acquire mass. This convenient particle is said to be largely absent at first, but then proceeds to spontaneously fill up space. This idea was based on Nambu's concept that the perfect beauty that initially exists in this world is then spontaneously lost. According to Weinberg, particles such as electrons are blocked by these Higgs bosons and find it more difficult to move. It is, in fact, this difficulty in movement that we experience as mass. Weinberg presented his paper in 1967. In it, he succeeded in attributing mass to electrons and weak force particles, using the idea of the Higgs boson. However, Weinberg's theory was met with skepticism at the time. And then a breakthrough came in 2012. More than 40 years had passed since Weinberg presented his theory. A massive experimental facility which can fire energy of unprecedented magnitude into a single point in space detected the signals for the Higgs boson.
We have a success today. We have a discovery. We have discovered a new particle, a boson, most probably a Higgs boson.
Weinberg's theory was finally proved right. The theory of the Higgs boson that it had been based on was also recognized and awarded the Nobel Prize. Physicists had finally arrived at the one and only formula. The standard model that explains the 4 types of elementary particles and the 3 forces that make up the universe was complete at last. In one corner of CERN, where the Higgs boson was discovered, a stone commemorates the formula thought to be the closest to the ultimate formula. It marked a culmination in the journey of physicists spanning 100 years. How is the beautiful symmetry of the ultimate formula reflected in the world around us? Physicists now understand the history of the universe since the Big Bang in the following way. The universe began according to the blueprint, that is the ultimate formula, and initially maintained the blueprint's perfect symmetry. At this point, all elementary particles were massless and flew around scattered. But then, as a result of the spontaneous breaking of symmetry brought about by the Higgs boson, elementary particles acquired mass. As a result of this acquired mass, particles were brought together to form atoms, and stars began to appear, creating galaxies. Even the fact that we exist in this world today is thought to have always been part of the ultimate formula. Thanks to the discovery of the Higgs boson, it is said that there is no phenomenon in this world that cannot be explained by the standard model. But instead of celebrating their great achievement, the physicists who developed the standard model are now working toward their next goal. Elementary particles are so light that it had never seemed necessary to consider the issue of gravitational force. Now, at the forefront of physics, there is the consensus that without taking into account gravity, the ultimate formula can never truly be discovered.
We are not just content with a mathematically elegant theory of weak, strong, and electromagnetic forces. We want it also to be a theory of gravitation. The idea of a unitary view of nature in which everything can be explained in terms of some deep fundamental laws, I think is new in the 20th century. That's a tremendous philosophical change, because it's a change in the kind of knowledge we want to find.
Physicists have spent hundreds of years trying to decipher the nature of the universe. The crusade for the ultimate formula continues to this day.